Section 5.5, Substitution. So we just learned about the fundamental theorem of calculus, and that theorem gave us tools for how to evaluate antiderivatives without the need for Riemann sums. It falls short, however, in cases where antiderivatives aren't easily found. This section is going to give us new tools for finding antiderivatives, specifically for functions where you're looking for the antiderivative of a function that had a chain rule derivative applied to it. So let's take a look at example 530. The function we're looking at integrating is 6x times 3x squared plus 4 all raised to the fourth power. We don't have a shortcut rule for this, so instead of resulting back to Riemann sums, we're going to try this new technique called U substitution. We're going to let u become our new variable, and it's kind of like an intermediate function. U is a function of x, and I want to pick u so that it looks like the inside of whatever function we are taking the integral of. So looking at our function, this 3x squared plus 4 is inside of the fourth power. So I'm going to pick the 3x squared to be my u function because it looks like an inside function. From there, I'm going to reverse my chain rule. So I'm going to find du dx of the u function. That becomes 3 times 2x plus 0, or rather du dx equals 6x. And then I'm going to try and create the differential for u. Now, let me explain why that's important. The original integral had a differential dx, but we're in the process of replacing x with this new variable u. So that means I need to rewrite my integral so that it has a du differential rather than a dx. So looking at this derivative, we're going to kind of imagine that du dx is like a fraction where I can multiply by dx on both sides. On the left, the dx divides off, leaving behind du. And then on the right, we have 6x dx. So this is the differential that we used to have, and this is the differential that we're going to now use. Now, we have to go back to our original integral and replace everything that has an x in it in terms of u's. And remember that u is technically a function of x, which is why we're allowed to do this. So looking at our integral, the 3x squared plus 4, we've already said that that is equivalent to u. We set it up that way. And then we notice that there is 6x dx, which we just calculated to be equivalent to du. So I'll pull out each one of those things and replace it with the appropriate u version. So we'll have u raised to the fourth power, and then instead of 6x dx, we will have du, and of course the integral needs to be copied down. So notice how we had a far more complicated function that we wanted to integrate. We did this u substitution process to create a new integral that's going to be much easier to integrate. This is just a polynomial. We're integrating with respect to u. You can really think of this as if it were the same x to the fourth dx function. But remember, x was already a variable that existed in this problem, so we don't want to use x in this new form. We're going to use the letter u to remind ourselves that we've swapped variables. So we integrate u to the fourth with respect to u. That becomes u to the fifth over 5. There are no bounds on our integral. That means this is an indefinite integral, so we need to include the plus c. And this is all of our antiderivatives for the function. However, because the problem started off with variables x, we should answer the problem with variables x. So now we're going to go back and back substitute, replacing u of x with the equivalent in x. Remember that we defined u to be the function 3x squared plus 4. So we will replace the u in our antiderivative with the equivalent. So we'll have 3x squared plus 4. That was all raised to the 5th power, so I need to write that in still, and it was all divided by 5. And of course, we still have the plus c. So this is the process of u substitution. It doesn't have to be the letter u, but this is the convention to use a u for the substitution. And it allows us to find antiderivatives for a function who probably resulted from a chain rule derivative. Example 5.31 requires a u substitution, again, to find the antiderivative. However, this time there'll be a slight alteration that's needed in the process. So we start just like before. Let's let u become this function of x. I'll pick the innermost function I can identify, so z squared minus 5. Oops, u is not going to be a function of x. Our original problem is written in terms of z, so we're replacing z with u, not x. So then I'll take the derivative of u with respect to z. That would become 2z. Multiply through by dz so that I can see du is 2z dz. Now looking back, I can easily see what I will pull out in terms of z to replace with the letter u. But as far as how to replace the differential dz with the differential du, notice that du isn't exactly showing up in our integral. Du needs to be 2 times z dz, and our integral doesn't have that multiple of 2, it just has the z dz. So we're going to do a small alteration. We would like for this du to be replaced seamlessly. So what I have in this white box, we need to alter it so that it matches what already appears in the integral. Basically, we're going to divide by 2 on both sides so that I can match up perfectly with what I have inside of my original integral. The 2's will divide off, leaving behind on the right-hand side of the equation z dz. And on the left-hand side, I'm going to look at that as 1/2 times du. So when I pull z dz out of my original integral, I will replace it with the equivalent 1/2 du. So I'll copy over my integral. Instead of z root z squared minus 5, we will have root u. And then I have 1/2 du replacing my z and dz factors. 1/2 is just a constant, so if you'd like, we can factor that out of our integral, so that we're really just integrating root u with respect to u. And if we'd like, we can even rewrite that root as a rational exponent, so u to the 1/2, and then we integrate this just like a polynomial. So 1/2 times u to the 1/2 plus 1, which becomes 3/2, which means I need to divide by 3/2. And again, there's no bounds on my integral, so this is an indefinite integral. I'm required to add the plus c to account for all possible antiderivatives. Now, before we go back to flipping things into terms of z again, let's clean this up the best we can. Instead of dividing by 3/2, let's flip that fraction and multiply. So now we'll have 1/2 times 2/3 times u to the 3/2 plus c. The 1/2 and the 2 from the numerator of 2/3, they simplify out, so I'm left with 1/3 u to the 3/2 plus c. And then last, now we can replace u with terms of z. So I'll have 1/3 u was z squared minus 5 raised to the power of 3/2 plus c. So sometimes when you do a u substitution, everything will work out smooth, no alteration needed. Other times you will have a small alteration, and of course there are other cases that we're going to have to consider as well.